Well, this is the second half of lesson number 4, Mathematics 4, on differential equations and transforms, and we're about to work some problems, the FE style exam problems in the manual. The first problem asks us to solve the following differential equation: y double prime plus 4y prime plus 4y is equal to 0. Initial conditions are given. There are two of them. Y of 0 is equal to 1, and y prime of 0 is equal to 0. There are a couple of ways to proceed with this problem. The conventional way is to use the usual differential equation methods for solving the problem, or we can use the Laplace transform method. So let's use, since we'll have the opportunity to use the Laplace transform method later in this session, let's use the conventional method now and do a classical differential equation solution. So we start off by saying, let's form the system's characteristic equation. We have r squared plus 4r plus 4 is equal to 0. This is a vital step, a very important step. When we factor this, we're going to get r plus 2 times r plus 2 is equal to 0, which says that the two roots, r1 comma 2, are equal to simply minus 2 and minus 2. We have repeated real roots. This is a critically damped system, repeated real roots. So what does the solution look like? The solution, y, will be equal to some constant, c1, times e to the r1 times x, plus c2 times e to the r2 times x. And notice that we must include, in this point, times x. This is c2x e to the power r2x. c1. Now we know that r1 is equal to minus 2, so we have minus 2x plus c2 e x. Let me reverse those. X e to the minus 2x. Well, we're virtually finished, except that we have these constants to be concerned about, c1 and c2. So in order to evaluate the constants, let's take the expression we have here for y and make a use of this initial condition. When y is equal to 0, when x is equal to 0, y of 0 is equal to 1, which in this case is equal to c1 plus 0, because since this is times x in here, this whole term gets wiped out when we set x equal to 0. So we already solved for c1. c1 is equal to 1. Now I want to solve for c sub 2. In order to do that, I need to take this equation now and differentiate it. And when I form its derivative, I'll take advantage of this second initial condition. So let's do a differentiation in this. I have minus 2 times c1 times e to the minus 2x when I differentiate. And then when I differentiate the second term, I get, now this is a product of two terms. So we'll put down it's the first, which is c2 times x, times the derivative of the second term, which will be e to the minus 2x with a minus 2 out in front. There's more. Plus c2 times e to the minus 2x, which is what we get now when we differentiate x with respect to x. Now if I take this expression, and I've done my differentiation correctly, and I set x equal to 0, I get, and I'll put it right up here, when x equal to 0, I get that y dot of 0, or y prime of 0, which is equal to 0, is equal to what we have here. With x equal to 0, I have minus 2 c1. This next term becomes 0 because the time is x, and the last term becomes plus c2. So I have that minus 2c1 plus c2 is equal to 0. Well, I already solved for C1. I know C1 is equal to 1. This becomes minus 2 plus C2 is equal to 0. Consequently, we see that C sub 2 is equal to 2. So there I have it. Now I can put into the solution at this point. This is the equation for the solution. C1 is replaced by 1, and C2 is replaced by 2. So the final solution should read